This is the video solution of questions from 41 to 50. The first question is 43 in this. The phase diagram for CO2 is given. In the phase diagram, this is the triple point. This particular part is the set of pressure, temperature conditions at which it will exist as a solid. This is for pressure temperature conditions of the liquid phase, and this portion is pressure temperature conditions for the gaseous phase. And the question says at 298 Kelvin is the normal boiling point of CO2. Now for normal boiling point, the vapor pressure has to become equal to external pressure. It has to become 1 atm. Now at 1 atm we have a value of 195 Kelvin, which would be the normal boiling point of CO2. In fact, it will not be a boiling point, it will be a temperature at which sublimation takes place. As you can see, CO2 will only exist in solid and gaseous forms as long as the pressure is below 5 atm, below this region. Once the pressure exceeds 5 atm, then at 5 atm there is a transition from solid to liquid, and CO2 may exist as a liquid as well. But below 5 atm, it only exists as in solid and gaseous phases. The second option says that 1 atm and 190 Kelvin CO2 exists as a gas. No, it will exist as a solid, I guess. If you take 190 Kelvin, which lies about here, and you want an intersection with the 1 atm line, you will get an intersection here, which is in the solid section. So under these conditions, CO2 will exist as a solid. The third option is that CO2 will sublime over 195 Kelvin under normal atmospheric pressure. Yes, if the temperature is above 195 Kelvin and we have 1 atm, a normal atmospheric pressure, then we have the gaseous phase. So it will undergo sublimation if it exceeds 195 Kelvin. The third, last bit is melting point boiling point of CO2 will increase on increasing pressure. That is correct. If you increase pressure, the value of temperature for the solid liquid transition increases. Higher pressure gives you a higher value of temperature, and the same is true for solid. The same is true for liquid gas transition as well. So when you increase pressure, both melting as well as boiling point of CO2 will increase. For question 44, we have A, B, and C, right? So you have 1 mole of A to start with. Okay. Now, see, B to C and C to A equilibrium constant values are given as K2 and K3 respectively, which are 0.4 and 0.6. If you add these two equations, we get the equilibrium constant. You add this up and you get the equilibrium constant. B is in equilibrium with A. So that turns out to be K2 into K3, which is 0.24. So the equilibrium constant for A is in equilibrium with B. The reverse of this equation will be 1 divided by 0.24. Divided by 0.24. That says we take 1 mole of A at the beginning, and the options here are, we'll find the value of K1, which is already done. Stability as per thermodynamics, we can look into this first. Now C to A has an equilibrium constant less than 1, which means C is more stable than A. Also A to B has an equilibrium constant which is greater than 1, so B is more stable than A. So isomer A would also be, should be the least stable as per thermodynamics. That part is done. Now we need the concentration of C at equilibrium, and A plus B plus C is equal to 1. And the first part is true. The first part is true because all conversions are in a 1:1 ratio. Let's say we start with 1 mole of A and you end up with 1 minus X moles of B at the first equilibrium. Then B will be formed as X. B gets converted to C. It starts from X. Let's say it becomes X minus Y. So C becomes Y. And from C to A, the conversion starts with C at Y. Let's say it becomes Y minus Z. So A, which was already 1 minus X, increases by Z. Now these are the final values that we have here. This A has to be updated, this B and this C has to be updated as well. Anyways, if you add the value of A plus B plus C, you'll get 1. That's because all conversions are in a 1:1 ratio, so the number of moles will not change during the course of the reaction. Option B at the last wants you to find the concentration of C at the attainment of equilibrium in all these reactions. Okay. And to find out the concentration of C, we can just use this equation. You just write that A plus B plus C concentrations have to be equal to 1 because of mass balance. And then see, individual equilibrium constant values are known. So you write everything in terms of C. Now from this equation we have C by B as 0.4. So B is 2.5 times concentration of C. So this becomes 2.5 C. Similarly for CA equilibrium, A by C is 0.6. So A becomes 0.6 C. This total is 1, so that gives you the concentration for C. Anyways, it cannot be 4.1, it cannot exceed the value of 1, so B is incorrect as such. Question 46 and 47 are questions on Le-Chatelier's principle. Okay, let's see. In question 46, it says decreases concentration of HgI for 2 minus. Okay, so addition of 0.1 molar Hi will add I minus and it will remove OH minus because the addition of H plus. So both of them will cause a shift in the forward direction. Addition of HgO solid because the solid will have no effect on the position of the equilibrium. Addition of liquid water. Now if you add liquid water, volume of the solution will increase. It doesn't matter that liquid water is a reactant in this case because the concentration of water, liquid water as such does not matter. But when you add the solvent, the concentrations of all the solute particles which are present, solute ions, that will decrease. And as concentration of the solutes decreases, the equilibrium will shift to produce greater number of solute particles or greater concentration of solute particles. Now the product has just 3 moles of solute particles, but the reactant has 4. So that will cause a shift in the backward direction and it will decrease the equilibrium concentration of HgI for 2 minus. Addition of KOH, aqueous KOH will increase OH minus ion concentration, which will shift the equilibrium in the backward direction. So that will also decrease HgI for 2 minus concentration. Right. So question 47, decrease of pressure. Now as you decrease pressure, the system will become less compact, it will expand. And as solid water is less dense compared to liquid water, decrease in pressure will cause it to shift in the backward direction. Now because more solid water has been formed, you will have to heat to a higher temperature for melting to take place. So the melting point temperature will increase. We have this paragraph question at the end. Constant for a particular reaction. Okay. Question 49 is above problem. So in 48, in a study of equilibrium, 1 mole of H2 and 3 mole of I2 gave rise to X. Addition for the 2 mole of H2 gave additional X moles of HI. What is X? Let's work this out first. So if initially you have 1 mole of this and 3 moles of this, then at equilibrium you end up with X moles of HI. So this must be 1 minus X by 2 and this must be 3 minus X by 2. Again, delta N is 0 for this question, so we don't have to bother about volume of the container. The addition of further 2 moles of H2 gave an additional X moles of HI. So if I add another 2 moles of H2, then the H2 concentration increases to 3 minus X by 2. This is still X, and when the new equilibrium is reached, then HI concentration increases by a further X value. If there's a further X amount of increase, then there has to be an X by 2 decrease in both H2 and I2 concentration. So they reach 3 minus X and 3 minus X values. This is the set of equations for equilibrium 1. This is set of equations for equilibrium 2. Now the equilibrium constant has to remain same, so we can write that K is X squared by 1 minus X by 2 into 3 minus X by 2, which should also be equal to the value from this second equilibrium. That is 2x squared divided by 3 minus X into 3 minus X. This should give you a value of X. Okay, so once the value of X is known, we can get a value of K, which is asked in question 49. In question 50, we have SO2 plus O2 giving you 2 SO3, and we started with 2 moles of SO2 and 1.5 mole of O2. So we initially had 2 moles of this and 1.5 moles of this. Equilibrium mixture requires 0.4 mole of KMnO4 in acidic medium. Now, as the reaction proceeds, some amount of SO3 will be formed, but some amount of SO2 will also remain unreacted. Now the SO2 which is unreacted will be oxidized by permanganate ion into sulfate. SO2 is in a +4 oxidation state and will get oxidized to a +6 oxidation state. SO3 is already in a +6 oxidation state for sulfur, so oxidation of SO3 will not take place. The same thing goes for oxygen as well. Now in this case, the N factor for MnO4 minus is its change in oxidation state from +7 to +2. So N factor for MnO4 minus is 5. That for SO2 is 2. So the balanced equation would ultimately look something like this. Now SO2 and MnO4 minus will react in a 5:2 ratio. And MnO4 minus required is 0.4 moles. So the SO2 which would be left is 5 by 2 times 0.4. So at equilibrium we can say that 1 mole of SO2 has reacted, so that 1 mole is left behind at equilibrium. Now this is a 2:1 stoichiometric ratio, so only 0.5 mole of O2 will be consumed, which is also left as 1. This is a 1:1 ratio for SO2 and SO3, so if 1 mole is consumed, 1 mole of SO3 will be formed. That gives you the equilibrium constant Kc. Okay, so you have a 5-liter flask. You write equilibrium. See, delta N is not 0 in this case, so the equilibrium constant will depend upon volume of the container. So the concentrations now are 1/5 for each of them. Use this to get the value of Kc.